we have this inverse trig function, which we can think of as an angle. So if tangent inverse of x is equal to theta, that's the same thing as saying that the tangent of theta is equal to x. So we'll draw a triangle where this is the case. We have our angle theta, and tangent, which is opposite over adjacent, needs to equal x. So we can just call our opposite x and our adjacent 1, and this is a triangle for which this equality works. And now we can use the Pythagorean theorem to solve for our hypotenuse. So if we call that y, we have 1 squared plus x squared equals y squared. So y is equal to the square root of 1 plus x squared. Now this function, this is cosine of theta. Cosine is adjacent over hypotenuse. So 1 divided by the square root of 1 plus x squared. And that is a simplified expression for this function.
Next, we will introduce a new function called the arcsecant of x. Let's recall the secant of x function and its graph. And let's answer the following questions. Is this function one-to-one? The answer is no, because it doesn't pass the horizontal line test. Does this function have an inverse? The answer is also no, because only one-to-one functions have inverses. Now, let's make a new function g of x from the secant of x function by restricting the domain of the secant function to the closed interval between 0 and pi. Is this function one-to-one? The answer is yes, because now it passes the horizontal line test. Does this function have an inverse? The answer is also yes, because all one-to-one functions have inverse functions. And here's what it looks like. What is this function? This function is not any of the functions that we already know, so we give it a name, the arcsecant of x function. Let's take a look at this new function and its graph. The domain of this function is all real numbers except the values that are between -1 and 1. And the range of this function is all the values between 0 and pi inclusive except pi over 2. We should be able to find the output of this function for any input in the domain using the graph or a calculator. We introduced a new function called the arcsecant of x and discussed some of its properties.
When we have inverse trigonometric functions, like the arcsecant here, we think of those as angles, call it theta. So this means that secant inverse of x equals theta, and we can rewrite this as secant of theta equals x. And what this does for us is it allows us to draw a triangle based on this relationship. We have an angle theta, and secant is hypotenuse over adjacent. So we'll call that x and 1. And we can solve for this third side by using the Pythagorean theorem. And we'll call that y. And 1 squared plus y squared equals x squared. And if we solve for y, we get the square root of x squared minus 1. Now, this expression that we're trying to simplify, this is the tangent of theta. And tangent of theta is opposite over adjacent. So that's the square root of x squared minus 1 divided by 1. So there's our simplified form of this function. Find the exact value of secant of the arcsecant of 1/2. And we can here use the very nice property of the inverse trig functions, that if you have a trig function of the inverse trig function, and that's the same one, then it just cancels out and you get this, this 1/2. Now you have to be very, very careful though, because that only works if this inner function is actually
defined. And this is super, super tricky because note, if you think of this as an angle and then try to write secant of the angle equals 1/2, that actually never happens. That's not even possible. Okay, the secant will never be 1/2 because that would mean that the cosine is 2. And the cosine of a function is never 2. And so this is not actually even possible, which means this arcsecant of 1/2 is not defined. So this is undefined or impossible.
If possible, find the exact value of each expression. Here we have the arcsine of -1/2. So in other words, we're looking for an angle whose sine is -1/2. In other words, this is equal to some angle, I'm going to call it theta, where sine of the angle theta is equal to -1/2. And we have this restriction that we know that the range of the inverse sine function is -π/2 to +π/2. So we're looking for an angle where the sine is -1/2. I'm going to go ahead and just draw our unit circle here. This is very sloppy. I'm actually going to redo this because it's going to. So here's our unit circle, and we're looking for when the sine is -1/2. Now the sine is -1/2 in a couple places on the unit circle. We've got right here and right here, and of course those could be multiple different angles depending on how many times you go around the circle and which direction you go. However, the arcsine will only give us something between -π/2 and +π/2. We're only allowed to have things there. So we have this angle here then. It's just going to be that angle right there that we're looking at, which is -π/6. -π/6. So that's the arcsine of -1/2. Okay, the inverse sine of √3/2. Again, this is an angle. And so we're looking for when the sine of some angle is equal to √3/2. So I'm looking for when that happens. And from our knowledge of the unit circle, okay, there's a place up here where the sine is equal to √3/2. And since we can only get things between -π/2 and π/2, we know that that's this angle right here, which is π/3. So the inverse sine of √3/2 is π/3. Okay, finally here, sine inverse of 2. In other words, if this would be some angle where the sine of that angle is equal to 2. However, we know that the sine has a range of -1 to 1. Sine will never give us a number outside that range. It can never give us 2. And so this has no solution. This does not exist. Does not exist. Okay, 2 is outside the domain of the inverse sine function. If possible, find the exact value of each expression. The arccosine of √2/2. So when we see an arc trig function or an inverse trig function, we should think this is equal to an angle. And this angle, this means that the cosine of that angle is equal to √2/2. Now, if we consider our unit circle, there are many places where the cosine is equal to √2/2, but they all look like the same. They're all coterminal with these two locations right here. And the arccosine is only going to give us a value between 0 and pi. So that's going to be anything here, okay? Anything in the first two quadrants. And so, of course, that's this angle right here, which is going to be π/4. The arctangent of 0, this is equal to an angle. And this means that tangent of the angle theta is equal to 0. So we want to know, when does the tangent equal to 0? And we need to remember that our arctangent will only give us a value between -π/2 and +π/2. So looking at this is sine over cosine. And if that's equal to 0, then that means that sine is equal to 0. So that tells me that I'm looking for a place between negative pi over 2 and positive pi over 2 where the sign is equal to 0, which of course is just right here at 0. So the arctangent of 0 is 0. Finally, the arctangent of negative 1. Again, if this is equal to an angle, I'm going to call it theta. We'll mix it up a little bit. This means that tangent of the angle, theta, is equal to negative 1. Well, this is, if I think of this as sine over cosine, I've got sine alpha over cosine alpha equals negative 1. And then multiply both sides by cosine alpha. We're looking for when sine of alpha is equal to the negative cosine of alpha. So looking at our unit circle, we're looking for when sine and cosine have the same value, but one's positive and one's negative. And since this is the inverse tangent, it can only give us something between negative pi over 2 and positive pi over 2. And sine and cosine have the same value here at this spot right here, but here the cosine is positive and the sine is negative. And up here though, they're both positive, so that doesn't work. So it's just this location right here, where that, of course, that angle is equal to negative pi over 4.
Find the exact value of cosine inverse of negative square root of 3 over 2. When we see an inverse trig function, we think of it as an angle. I'm going to call it theta. And then we can think of this now in terms of the cosine function. This is the same thing as saying cosine of theta is equal to negative root 3 over 2. And so we're going to look at our unit circle, and we're looking for places where the cosine is equal to negative square root of 3 over 2. So you look at your memorized unit circle, and hopefully you've got it memorized, and we find that that happens in two places. Okay, it's two angles that look like this. And the two angles where that occurs, we have 5 pi over 6, and we have 7 pi over 6. But the cosine inverse function has a specified range. Okay, the inverse cosine is stuck between 0 and pi. And so we can draw that. That just means we can only kind of do this. We can't be anywhere outside of what this arrow shows. So we certainly can't have this 7 pi over 6. That's not okay. However, this angle here of 5 pi over 6, that is that angle there. And so that is a valid, that's our valid output for this. And so this cosine inverse of negative root 3 over 2 is 5 pi over 6. Find the exact value of arcsecant of the square root of 2. Well, the arcsecant of the square root of 2, that's an angle, some angle theta. So we can think of it as secant of the angle is equal to the square root of 2. And secant, actually, we can say, well, this is 1 over cosine. 1 over cosine. And then we can actually just find cosine here. So if I multiply both sides by cosine, and then divide by the square root of 2, I have cosine of theta equals the 1 over square root of 2. Now, this never shows up on the unit circle, but on the unit circle, everything's rationalized. So if we multiply by root 2 over root 2, we get root 2 over 2. And that certainly does show up on the unit circle, right? So we have a circle, and when cosine is square root of 2 over 2, well, that happens here at pi over 4 and at 7 pi over 4. Now, we're looking at, this was for cosine, but of course we're looking at the original secant, arcsecant. And arcsecant, the restriction on that is pretty much the same as the arc cosine, in that it's only going to give us something in the first two quadrants. And so we're only allowed angles that are these angles here. I cut out pi over 2 because secant of pi over 2 is not even defined but everything else over here is. So we can't use the 7 pi over 4, but pi over 4 we can. And so pi over 4 is going to be the solution here. Find the exact value of the arc sine of -1. So this inverse sine function, anytime you see an inverse trigonometric function, you want to think of that as an angle. I'm going to call it theta. And you can think of this as saying, this is equivalent to saying that the sine of theta is equal to -1. So then we look at our unit circle. And on our unit circle, we're looking for a place where the sine is equal to -1. Now, hopefully you've got your unit circle memorized. Remember that the sine is the y-coordinate. So a y-coordinate of -1 is actually down here at this point. Now, you need to be careful because that point, if you're just thinking of your unit circle, most people would think of that as this angle right here, which is 3 pi over 2. However, the inverse sine function, the arc sine function, is stuck between -pi over 2 and pi over 2. And drawing that, that means from 0 we can go this way or we can go this way, and we cannot go past those. So we can't actually go this way and pass up that red arrow. We can't do that. Instead, we have to get to that location by coming down this way. And so that angle right there, that's -pi over 2, which of course is in this range. And so that's what the arc sine of -1 is. That is -pi over 2.
Next, we will introduce a new function called the arccotangent. Let's recall the cotangent of x function and its graph. And let's answer the following questions. Is this function 1-to-1? The answer is no, because it doesn't pass the horizontal line test. Does this function have an inverse? The answer is also no, because only 1-to-1 functions have inverses. Now, let's make a new function, g of x, from the cotangent of x function by restricting the domain of the cotangent to the open interval between 0 and pi. Is this function 1-to-1? Yes, because it passes the horizontal line test. Does this function have an inverse? Also yes, because all 1-to-1 functions have inverse functions. And here's what it looks like. What is this function? This function is not any of the functions that we already know, so we give it a name, the arccotangent of x function. Let's take a look at this new function and its graph. The domain of this function is from -infinity to +infinity, and the range of this function is from 0 to pi inclusive. We should be able to find the output of this function for any input in the domain using the graph or a calculator. However, the outputs for some nice inputs we should be able to figure out analytically. For example, let's find the arccotangent of 1. We're looking for some value that is between 0 and pi, such that the cotangent of that value is 1. There are infinitely many values for which the cotangent is equal to 1. However, only one of them is in the desired interval. Therefore, the arccotangent of 1 is pi over 4. Let's find the arccotangent of the cotangent of 4 pi over 3. We're looking for some value that is between 0 and pi, such that the cotangent of that value is the same as the cotangent of 4 pi over 3. There are infinitely many values for which the cotangent is equal to the cotangent of 4 pi over 3. However, only one of them is in the desired interval. Therefore, the arccotangent of the cotangent of 4 pi over 3 is pi over 3. We introduced a new function called the arccotangent and discussed some of its properties.
Find the exact value of arccotangent of the square root of 3. For this, this is an inverse function, inverse trig function, so it's equal to an angle, theta. And we can write this using just the cotangent function. Cotangent of theta equals the square root of 3. And so what we need to do is look at our unit circle and find a time when the cotangent of an angle is equal to the square root of 3. Now, I'm not going to go and do all of the angles where this is true, but like go through all the angles and actually compute this. What you do need to know though is that cotangent is cosine over sine. So you would go through and take the x coordinate, which is cosine, and divide by the y coordinate, which is sine of each point. And you're looking for that square root of 3. Now that happens in 2 spots on the unit circle, and I should say in 1 revolution of the unit circle. It's at pi over 6 and 7 pi over 6. But like all inverse trigonometric functions, we have a restriction on the range of the arccotangent. And this range comes from where the asymptotes of the cotangent function are. The asymptotes of the cotangent function are at pi and at 0. Okay, and so we need our answer here to be between those two things. So it's this is the range we're looking at, and so obviously the 7 pi over 6 is not valid, and so we only use the pi over 6. So the arccotangent of the square root of 3 is pi over 6.
Next, we will introduce a new function called the arccosecant. Let's recall the cosecant of x function and its graph. And let's answer the following questions. Is this function one-to-one? The answer is no, because it doesn't pass the horizontal line test. Does this function have an inverse? The answer is also no, because only one-to-one functions have inverses. Now, let's make a new function g of x from the cosecant of x by restricting the domain of the cosecant function to the interval between negative pi over 2 and pi over 2. Is this function one-to-one? The answer is yes, because it passes the horizontal line test. Does this function have an inverse? The answer is also yes, because all one-to-one functions have inverse functions. And here's what it looks like. What is this function? This function is not any of the functions that we already know, so we give it a name, the arccosecant of x function. Let's take a look at this new function and its graph. The domain of this function is all real numbers except the values between negative 1 and 1. The range of this function is the values between negative pi over 2 and pi over 2 except 0. We should be able to find the output of this function for any input in the domain using the graph or a calculator. We introduced a new function called the arccosecant of x and discussed some of its properties.
When we have inverse trigonometric functions, sometimes we're going to see composition of a trigonometric function with an inverse trigonometric function. And normally inverse functions, when you compose when you do a composite between a function and its inverse, they just cancel each other out and you get back x. Okay, and unfortunately, that's not going to always be the case for us with inverse trigonometric functions because we have to place those restrictions. And so the functions themselves, sine, cosine, tangent, and so on, they're not actually invertible functions. And so not all the properties always hold. So this property here in particular is the one that's not always going to hold. F inverse of f of x. This normally is equal to x, okay? But it will not hold within trigonometric functions, okay? However, this will always equal x, okay? Always. So that's really nice, okay? Let's go ahead and just see how that comes into play. So right here, I should say always if x is in the domain of f inverse, okay? So that's the only thing you would need to check here. So here I've got tangent of the arctangent of negative 5. So that's looking like this, function of an inverse function of x, okay? Now negative 5, what you need to check is negative 5 in the domain of the arctangent. And the arctangent has a domain of all real numbers. You can plug anything you want in. If you remember the graph, it looks like this, okay? where you can plug any number you want in. And so -5 is in the domain of arctangent. So then the tangent and the arctangent will just cancel each other out. And this is equal to -5. Okay, let's look at this part B here. Here it's flipped around. I've got the arc sine of the sine of 5 pi over 3. So this is like this first one, and that's not always equal to x. So we had to do some work. And all we do is we work our way from the inside out. So we start off by doing this inside, what's the sine of 5 pi over 3? So based on our knowledge of the unit circle, we do that. Sine of 5 pi over 3 is -√3 over 2. Okay. And then, now we're doing the arc sine of -√3 over 2. So what we do is we look at where do I have an angle where the sine is -√3 over 2. And there are two places that happens, down here and down here. But the arc sine only gives us a number between -pi over 2 and +pi over 2. So it has to be this angle right here. And you'll notice that this angle, this is in the same location as 5 pi over 3. Okay? And that's no accident. So here I've got that angle, which coterminal with 5 pi over 3 down here is between -pi over 2 and pi over 2 is -pi over 3. Okay, so you can see then that that the inverse outside with the function inside, those don't just cancel out. We have to do a little bit of work. Okay, and finally here we've got cosine of the cosine inverse of pi. And this looks like this f of f inverse. Now, this is always equal to x, as long as x is in the domain of f inverse. So we look at this and we say I have cosine inverse of pi. Well, cosine inverse has a domain of -1 to 1. Pi is outside of that, which means there's nothing we can do because this right here is undefined, which means the whole thing is undefined. Undefined or does not exist. Here we're doing composition of trigonometric and inverse trigonometric functions, but they're different functions. And so we need to be able to deal with that. And this is actually not too difficult. What we're going to do is actually use some triangles. So when we see an inverse trigonometric function, we want to think of that as some angle. I'm going to call it beta. So I've got that the cosine of the angle beta is equal to 2/3. And then I'm just going to draw a triangle. Draw a triangle where that's the case. Okay. And of course, it doesn't have to be to scale or anything. So I've got my angle beta. Cosine is adjacent over hypotenuse. So I can just do 2 and 3. And then solve for this other side using the Pythagorean theorem. Okay, so this side here, if I call that, actually we'll call it b. Then I've got a squared plus b squared equals c squared. In other words, 2 squared plus b squared equals 3 squared. So this is b squared equals 9 minus 4, which is 5. So b is equal to the square root of 5. Okay, so that's this here. And now we just go back and say, okay, now I'm doing tangent of that angle. Tangent of this angle, which I called beta. Well, tangent is opposite over adjacent. So that's the square root of 5 over 2. Okay, now notice that I drew here a triangle that you could think of as being drawn in standard position, this angle. And so this angle ended up being in the first quadrant. Okay, that is actually pretty important because we know that the arc cosine will only give us an angle in the first two quadrants, quadrants 1 and 2, something between 0 and pi. And so it's important that we are consistent with what that angle is going to look like, where it's going to be. All right, here we've got cosine of the arc sine of -3/5. So again, we're going to look at this angle here, and we're going to give that a name. I'm going to call this alpha. So this tells us that sine of the angle alpha is equal to -3/5. And then I'm going to draw a triangle. Now, what's important here is I'm going to draw it so that it's in the proper place. I know that the arc sine will only give me an angle in between -pi over 2 and pi over 2. And if it's negative, that's going to be down below. So it's actually down, looking like it's down here. Okay, I've got my angle alpha. Now sine is opposite over hypotenuse. So I could do opposite, -3 over hypotenuse 5. And then I can, of course, find my other side right here. And this side, well, we'll call that a squared plus negative 3 squared is equal to 5 squared. So we got a squared plus 9 equals 25. So a squared is equal to 16. And a is equal to 4. Now notice it could be positive or negative 4, but I knew that I was drawing this angle in the fourth quadrant, really, right? If I were to think about drawing kind of a circle like this. That's kind of what it was looking like, okay? And so I knew that that length there needed to be a positive. Okay, so this is equal to 4, and then I can say, now I can do the cosine of that angle alpha. Cosine is adjacent over hypotenuse, so that is 4 over 5.
We'd like to go ahead and just simplify this expression. We don't want trig functions, so we're going to do our processes before and do this. So this arctangent of x over, or sorry, arccosine of x over 2, we can write that, we think of that as an angle, and we can write this as cosine of that angle equals x over 2. All right, so we're going to draw a triangle where this is the case. And so my triangle I'm going to draw looks like, something, doesn't really matter how you draw it, but you've got your angle theta, and cosine of an angle is adjacent over hypotenuse. So we can do adjacent as x and hypotenuse as 2. And then we can solve for this other side. And this other side, well, I'll call it a, and then use the Pythagorean theorem. A squared plus x squared equals 2 squared. And then I can solve for a. So a squared equals 4 minus x squared, and then take the square root. So a equals the square root of 4 minus x squared. Now I'd like to point out here that when I did the square root, it would be a plus or minus. However, we know that the arc cosine only gives us something in either the first or second quadrants. And for both of those, the opposite side would be a positive. And so I'm only using the positive here. Now that I have that, I can find the tangent. The tangent of that angle is opposite over adjacent. So square root of 4 minus x squared, and then over the adjacent, which is x. And so there's our algebraic expression in which we don't have any trigonometric functions.
Here I've got some composition of trigonometric and inverse trigonometric functions, but I've got variables. And so I can't really evaluate it, but I can rewrite it as an algebraic expression without any trigonometric functions. So what we're going to start off with is we're going to draw a little triangle where this arc cosine of 3x, that's some angle. I'm going to call that angle theta. Okay, so this means that cosine of the angle theta is equal to 3x. And then I can draw a triangle like that. Now, we're told here that x is between 0 and 1/3. That's important to know because I have cosine is equal to a positive number. And so when I draw this, well, I know that the arc cosine is always between 0 and pi, but because I know that x is between 0 and 1/3, I know this cosine is a positive number. It's going to have to be in this first one. So I draw my angle, okay, and then I can say, well, now I've got this angle theta. Cosine is adjacent over hypotenuse, so I can just call adjacent 3x and the hypotenuse 1. And then I can solve for this side over here. We'll call that b. And use the Pythagorean theorem. 3x squared plus b squared equals 1 squared. So this is 9x squared plus b squared equals 1. And then we subtract the 9x squared over 1 minus 9x squared. And then we solve for b, take the square root. Now when you do a square root, normally you get a plus or a minus. However, based on our location here in the first quadrant, we know that b will be a positive. All right, so now I have b. I'm trying to find the sine of this angle theta. And sine is, of course, opposite over hypotenuse. So it's that b value. So square root of 1 minus 9x squared. All right, so for part B, same idea. Same idea, but we've got here the arc cosine of 2x over 3. That we're going to call the angle, we'll call it beta. So this says that cosine of the angle beta is 2x over 3. Because x is between 0 and 3/2, this thing here is between 0 and 1. And if the cosine is between 0 and 1, then I know I'm somewhere here to the right. And of course, the arc cosine can only give me an angle between 0 and pi over 2. So I have to be in this first quadrant. And then I can just draw a little triangle. It doesn't matter how I draw it, really, as long as it's in the proper quadrant. And my angle beta, now cosine is adjacent over hypotenuse. So I could just call the adjacent 2x and the hypotenuse 3. And then solve for this side over here. We'll call that b and use Pythagorean theorem. 2x squared plus b squared equals 3 squared. So this is 4x squared plus b squared equals 9. And then subtract the 4x squared. We get b squared equals 9 minus 4x squared. And then take the square root. And again, when we do a square root, we get a plus or a minus. We pick which one based on what quadrant we're in. And in this first quadrant, this b value is going to have to be positive. So it's the positive square root of 9 minus 4x squared. All right, and then we are doing cotangent of that angle. And cotangent of an angle is adjacent over opposite. And so here I say, well, adjacent is 2x. And opposite is b, which is that thing there, the square root of 9 minus 4x squared. Okay, so this is actually a really powerful tool. It's actually particularly useful in some applications in calculus, where you've got these trigonometric functions and inverse trigonometric functions, okay, and the composition of those, and actually being able to write those in algebraic form without any trigonometric functions. That's being able to kind of go between those forms is actually a very useful skill.
Find the exact value of sine of the inverse tangent of 3. Well, inverse tangent of 3, that we can think of as an angle theta. In other words, tangent of that angle is equal to 3. Now, we can draw a triangle here where the tangent of that angle is equal to 3. And this is not to scale, so don't think that it is. We've got an angle theta, and the tangent of it needs to be 3. So opposite over adjacent needs to be 3. So that's opposite could be 3, and the adjacent could be 1. Again, not to scale. But now we have a triangle where this is true, and we want to find the sine of the angle, and sine is opposite over hypotenuse. So we need the hypotenuse here. We'll call that c. And we can use our Pythagorean theorem. 1 squared plus 3 squared equals c squared. And that's 10 equals c squared. So c is the square root of 10. And now I can find the sine of that angle. The sine of the angle theta is opposite over hypotenuse. And that's it.
In this video, I will go over the homework that follows the lecture on Introduction to Inverse Trigonometric Functions, and as always, I hope you watched all these videos, and I expect you to be familiar with all 6 inverse trigonometric functions. So let's go ahead and get right into the homework and see what type of problems we are expected to do. So first problem is we have cotangent inverse of cotangent of 5 pi over 3, and as it can be very tempting to just, reduce this, we cannot do that for the same reason we cannot do this when working with composition of inverse functions. You cannot reduce this and this because that will imply that the answer is -2, but the domain of the radical function is only positive values. So how do we answer this question? Well, first we need to check the domain of cotangent inverse. And what's the domain of cotangent inverse? The answer is right here. So the domain of cotangent inverse is from, I'm sorry, not the domain, the range. We're looking for the range in which the outputs of cotangent inverse are expected to be in. And it says 0 to pi. So we expect whatever this number is to be between 0 and pi. So we're looking for some value whose cotangent is, well, it's fair to say we can label it as theta, but it doesn't matter. So we're looking for theta whose cotangent is equal to cotangent of 5 pi over 3, but the angle itself is between 0 and pi. And it's just a matter, I guess, of understanding what this angle is. So let's just sketch a quick unit circle, or just a circle. Where's 5 pi over 3? This is pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, right here. So you see how 5 pi over 3 is right over here. And we want, what's the cotangent of 5 pi over 3? It's the cosine of 5 pi over 3 divided by sine of 5 pi over 3. So I think what's important here is that it's going to be cosine of 5 pi over 3, it's 1/2. Sine of 5 pi over 3, it's negative root 3 over 2. So the question is, for which angle between 0 and pi, cotangent is going to be the same as this one? And the answer is, it's going to be the angle in second quadrant, and it's going to be precisely this angle right over here. So the answer is 2 pi over 3. So let's do 2 pi over 3. Similar problem, but with sine. So we have sine inverse of sine of 4 pi over 3. And the range of sine inverse, we can check. The range of sine inverse is from negative pi over 2 to pi over 2. So whatever this answer is, we can label it as theta. Theta must be between pi over 2 and negative pi over 2. And sine of theta has to be equal to sine of 4 pi over 3. So again, sketching a quick unit circle, 4 pi over 3 is right over here. And sine of 4 pi over 3 is the y-coordinate. And the question is, which angle between negative pi over 2 and positive pi over 2? So which angle in these two quadrants has the same sign? And the answer is, it's going to be the negative pi over 3. So this angle has exactly the same sign as this angle. But this angle satisfies this condition. So the answer is negative pi over 3. We have cosecant inverse of cosecant 4 pi over 3. The range of cosecant inverse function is So the range of this function is from negative pi over 2 to pi over 2, except 0. It cannot be equal to 0. So it has to be from pi over 2 to negative pi over 2, and it cannot be equal to 0. So these are the conditions that theta has to satisfy, in addition to cosecant of theta has to be equal to cosecant of 4 pi over 3. Now, an alternative approach to unit circle will be to actually graph this function, and let's go here and try Desmos. So we're looking for a value between negative pi over 2 and pi over 2 that is equal to cosecant of 4 pi over 3. So let's graph the function. So we have cosecant of x. We want the output to be equal to cosecant of 4 pi over 3. But we want our x to be between negative pi over 2 and pi over 2. So this is what we're doing. And the question is, for which value in this range the cosecant is equal to the cosecant of 4 pi over 3. And you can see that it's negative pi over 3. So this is the answer. I think I accidentally closed out the homework. Did I? So the answer here is negative pi over 3. So the range of cosecant, again, is from pi over 2 to negative pi over 2. Theta cannot be equal to 0, but cosecant of theta must be equal to cosecant of 5 pi over 3. And I'm going to use Desmos again, because it just seems to be easier. So I'm going to change this 4 to 5. And the answer is now negative pi over 3. Again, hold on, did anything change? Changing 4 pi over 3 to... because the cosecant of 4 pi over 3 and 5 pi over 3 is the same, so nothing changes here. The answer is still negative pi over 3. That makes sense. We have these expressions that we have seen before. There is a certain steps that we take to simplify them. And the first step is to introduce angle theta, so that the problem is now very simple. It's cosecant of theta. But what is theta? Theta is a value whose cotangent is equal to 3x minus 4. And I'm going to write it over 1. And now we're going to use the definitions of cosecant and cotangent to introduce the reference triangle. Cotangent is adjacent over opposite. And cosecant is hypotenuse over adjacent. So we're going to draw a triangle, and we're going to use with angle theta, and we're going to use this to label the opposite side as 1, the adjacent side as 3x minus 4, and then we're going to use the Pythagorean theorem to find the hypotenuse. And now we are ready to write the answer. So the cosecant theta will be the hypotenuse, which is 3x minus 4 squared plus 1, divided by adjacent side, which is 3x minus 4. So let's type the answer. We have square root of 3x minus 4 squared plus 1, all that divided by 3x minus 4. So let's see if we got the right answer. Cosecant is, guess it doesn't help to make this silly mistakes. Cosecant is actually over the opposite side, right? So we divide over 1. All right, let's do another one. It's again standard problem, standard procedure. Introduce angle theta. The problem is very simple. I need cosine of theta. Cosine of theta is adjacent over hypotenuse. So we draw a triangle. Here's theta, here's adjacent, here's hypotenuse, here's the opposite side, but I don't know any of these sides. So I need to use the fact that cotangent of theta is 5x minus 4 over 1, but cotangent is the adjacent over opposite, so I'm going to label my adjacent side as 5x minus 4. I'm going to label the opposite as 1, and by Pythagorean theorem, the hypotenuse is square root of 5x minus 4 squared plus 1. And I'm ready to write the answer. It's going to be adjacent side, 5x minus 4, divided by the hypotenuse side, which is square root of 5x minus 4 squared plus 1. We have another one. We have cosecant of cosine inverse 2x minus 4. We introduce angle theta. The problem is simple. We have to find cosecant of theta. Cosecant of theta is hypotenuse over opposite. I'm sorry, right, so this is cosecant. And we need to draw a triangle with angle theta. This is my adjacent, this is my opposite, this is my hypotenuse. And now I'm going to use the fact that cosine of theta is equal to 2x minus 4 over 1. And the fact that cosine is adjacent over hypotenuse. So I'm going to label the hypotenuse as 1 and adjacent side as 2x minus 4. And then by Pythagorean theorem, the opposite side will be 1 minus, well, the square root of 1 minus the square of 2x minus 4. So the answer is 1 over the square root of 1 minus 2x minus 4 squared. So 1 divided by square root of 1 minus 2x minus 4 squared. We have tangent secant inverse of 4x plus 2, and we introduce angle theta, so the problem is easy now. Tangent theta, which is opposite over adjacent, we draw a triangle. This is my opposite, this is my adjacent, this is my hypotenuse. Now we're going to use the fact that secant theta is 4x plus 2 over 1, and the fact that secant theta is hypotenuse over adjacent. And I'm going to label the hypotenuse as 4x plus 2 and adjacent as 1. Then by Pythagorean theorem, I'm going to use the Pythagorean theorem to find the opposite side. And now I'm going to write the answer. So it's going to be square root of 4x plus 2 squared minus 1 divided by 1. So it's just going to be the square root of 4x plus 2 squared minus 1. And we finished it. So if you have any questions about this homework, please reach out.